But I take the opportunity, of course, to thank our fantastic host and great organizer for this great event, which slowly creeps toward the end. And so that's the bad news. And we'll discuss about creeping, I guess, tomorrow. So this is, I think, lecture number 4, following Colby, McLeish, and Narita on dynamics. Here we'll focus on colloids, and this is brief but also very partial introduction because it is impossible, of course, to cover many topics in a short period. And for further discussion, this is what I call my social media reference. Okay, we'll say a few basic things about suspensions and suspension rheology. I take it that for many of you, those are known, but maybe not for everybody. And then we'll focus a little bit on the second item, tailoring properties through interactions and molecular manipulation. I will explain what this means, and we'll go slowly to arrested states. For sure, we won't have time to cover gels, but they were beautifully covered by Emanuela yesterday. And of course, there will be some extra notes in the slides that they will be available to you. Those who are interested on the topic can certainly consult the 2 books by Wagner and Mevis. They're about 10 years apart. The first one covers very basic elements, and the second is basically a collection of chapters edited by different people on the topic, more advanced. And I made a special note here to my friend and longtime collaborator, Michel Croat. Some of the material that I will discuss today is taken from our chapter there. Okay, so let's start with spheres. Before that, we should define the colloid. I'm in a privileged position to tell you that it's a Greek word. Kolla means glue. And so the idea is that the species are dominated one way or another by attractive interactions. Typically, their size is sub-micron, although if you have a 2 or 3 micron particle, this can certainly be a colloid. They are suspended in the medium, but the idea is that gravity is not important, although it may not be negligible. And here, for this simplicity, we are going to focus on spherical particles. So I took this from Wikipedia, so you can find, as you know, all sorts of things. So they have 3 different types of dispersed phases, gas, liquid, solid, and they have also 3 different types of medium phases. Of course, the interesting thing for us, the majority is this part here, when solid particles, solid spheres are dispersed in a liquid medium. Now, in Wikipedia, this region here is filled, all right? So then they consider also a suspending medium which is solid. I think it's at least misleading, so I decided to remove it. And my suggestion is we should be careful with Wikipedia. Nevertheless, let's start with reference to Professor Grossberg's first talk, or Professor Rubinstein's. It doesn't matter, on the thermal systems. You remember the thermal polymers and the fact that there are excluded volume interactions at the size scale of the monomer. So now here, this can be considered as one monomer, so it's going to be one sphere. And so then the hard sphere interactions, as we know, are those where there is nothing going on until the spheres touch each other. And so this is really the way this is described. This is well known. So far, so good. Problem is that referring to experiments, and this will be the focus of the discussion today, an experimental viewpoint at this problem. This is mission impossible. You can never have this thing. Here you always have some kinds of interactions, but the best thing to stabilize such particles is by grafting a tiny layer, and we'll come back to this in a minute. So now I'll show you here the zoo of interactions with colloidal particles. So this is hard spheres, and you see already indicated that there are nearly hard spheres. They have this tiny grafted layer here, which helps stabilizing against, for example, van der Waals interactions, and that's why you see that you have this little kink here in your potential, and this here relates to the response of the stabilizing layer. And so then we can induce attractions. In the attractions, our potential, of course, will be negative. And there are different ways to do this, but I would like to make reference to the different lectures that you heard all this previous period. So whenever you see names of lecturers in parentheses in blue, this is my reference to their lectures. So then we know already, if we ask the question how you can do this, that's easy, right? So the way that this is stabilized is because this layer fills a good solvent environment or a thermal solvent environment in the suspending medium. So if this is not the case, by changing the conditions, okay, and so you can easily work on lecture of Rubinstein, lecture number 1, if I remember, where basically you deal with polymer-solvent interaction, the real change, if you remember, and so then change the conditions and make your particle sticky. And of course, you have van der Waals interactions and so on. So now the interactions which I hope I will go to is those ones here, which were alluded a little bit by Emanuela in her first lecture, depletion interactions, because they are important in terms of what I mentioned, manipulation. And of course, then we have the charge interactions, and again, both Manuel and Shura Grossberg discussed them in different contexts, and so this is the well-known DLVO potential, and actually this is exactly what Emanuela showed in her first lecture. Okay. But we are going to focus in those areas, because there is no time to cover everything. Okay, let's go back to experiments and say that I would like to make a suspension of hard spheres, insisting it's experimental hard spheres. Certainly the most successful model system, now we start talking about model systems, is the so-called PMMA, polymethyl methacrylate hard sphere. So this is a well-known polymer of high Tg, about 100 degrees. And so then they effectively, one way to make it is to put in conditions of bad solvents. So then it's going to shrink, if you remember, make really this effective hard sphere. But then, in order for it to remain suspended in a medium, you have to stabilize it. So the typical stabilization polymer that is used is this polyhydrostearic acid, which has this funny form here. In fact, in reality, there is a comp polymer, so that means there is a chain with different grafts and so on, which is added. So there is a lot of important chemistry added into it. But at the end of the day, you create something that we can basically represent by this one here. So now, when you make such particles, and you need to characterize them, then I will come back to this in a minute. You can, first of all, see them by eye, because now we say that we are in the order of hundreds of nanometers, or maybe a few microns. Okay, typically people see them by confocal microscopy, and this is such an image here at a volume fraction of 0.45, and we'll come back to what the volume fraction means. There are interesting reference here for you, but for those interested, there is this classic review by Peter Pusey, certainly a pioneer in the field from '91, but I will somehow relate to what Ralph Colby mentioned, referring to the Green-Tobolsky paper. Of course, this is not solved, but certainly this stood the test of time. It remains classic reference for introducing hard spheres to those interested. I have in question mark here characterization. As I mentioned, this is really the model experimental system. there are hundreds, if no more, of publications using PMMA particles. But if you ask how well those particles are characterized, what do I mean by this? Look, people have suspended them in decalin, dodecan, dioctyl phthalate, squalene, and there are even more and so on. I think the answer is we don't know. What does it mean? It means that you need, first of all, to take your polymer, understand the solvent conditions for the polymer, then graft it on the particle, understand the solvent condition for the particle. All people typically do is take a particle in a dilute solution, and we'll see, or suspension, we'll see exactly what we get out of this. Okay, and so then there are interesting consequences of this, which I will allude to when we go to concentrated suspensions. But this will be our horsepower. So now if you ask what is the volume fraction of hard spheres, that's easy, right? This is basically the number density, right? Number over volume, and this is of course the volume of the particle. I write this with a little n here, and so this is typically the definition of volume fraction. The caveat is that there are issues here. As I mentioned, you need to measure the radius. Okay, so then this is the first thing. And I'm talking about the radius of the entire particle, right? The particle with the shell. And this is actually what I mentioned here. The second one is polydispersity. Much like in polymers, there is no perfect experimental system. You may recall that Professor McLeish discussed about some weird polymers. They are ring polymers. It doesn't matter. We don't talk about rings here. But behind this is basically the concept that it's impossible at the experimental scale to have the absolute system. And this is one of the many reasons why molecular simulations are so important. You know in what you have in your computer. Okay, so now what do people do to account for those issues, let alone to really estimate exactly the number average? I will come back to this in the minute when I say something about the phase diagram. So now let's look at some scales which will be useful. So first of all, we start with diffusion. Yep. Thibault, in my opinion, there is no clear answer, 5% or 10%. It is in this range, but I will come back to this when, first of all, I will tell you the standard way, which I'm sure you know, to estimate the volume fraction, and then we're going to discuss divergence of viscosity as this increases. Because an important question, let me make one point here. Typically, the stabilizing layer, let me go back to this. Okay, so this is a particle, all right, with stabilizing layer. The layer is very short, is crew cut, pretty much like me. So people use the same polymer, the same size of polymer, for different sizes of the sphere. And that already introduces a problem, right? Because this means that this bump here will be affected, right? And this is one of the fine experimental issues that people face. So I would say that if one wants to have a number, one should be on the order of 10%, but as I mentioned, it's really very much problem dependent. Okay, yeah. Numbers. So the first one is Brownian motion. So this you know because it has been discussed by Ralph and by Tetsu and others. So this is the time for the particle to move randomly by its size, right? And so that's the diffusion. It's given by Stokes-Einstein relation, and it's this expression. And so here I have you just for you to test. I give some typical numbers, and then you can estimate the time. All right. So now the other thing to worry about is this sedimentation that I mentioned, okay, the gravity effect. So here you have the gravitational force This is the delta rho, is the density difference of particle to suspension, and this is again the Stokes law. And so then using for velocity the distance equal to the size, you can estimate a characteristic time. And again, you can get numbers from this. Okay? So this is also something that's important to remember. And finally, we are going to restrict the discussion here to what we call low Reynolds number hydrodynamics. So this means that inertia is not important in the system. Whenever we have flow, it will be what we call a laminar flow. So if you wish, a slow flow, all right? So those are typical scales. So now there is a point I would like to make, and that relates also to other lectures that you heard before. Engineers like me like dimensionless numbers, right? So there is plenty of them here, but there is a reason for this. And so let us, and I will explain in a minute. So this is Monsieur Peclet, another great French scientist, after whom the Peclet number was introduced. So this is the product of the shear rate. You remember what shear rate is. Professor Kolbe explained this, right? So if and then the characteristic time, the diffusion time that we just saw. So in this kind of experiment, so when I take my suspension and I'm going to interrogate it by basically you may remember the two plates, moving one plate with a constant velocity, and therefore introducing a velocity gradient, which will give me the shear rate. The shear rate is the inverse characteristic time of observation, right? So that's very important, right? So I set the shear rate as an experimenter. The material has its own characteristic time, so then the inverse rate is basically the time of my observation. That's why I say that there is an observation time that relates to the material behavior. So now, in more general sense, Carl Weissenberg introduced, well, actually a similar concept, which of course was then named Weissenberg number. So it's the same thing. T is not necessarily different from T0, okay? But the Peclet number is restricted, at least per definition, to the characteristic time of the diffusion of the single particle, whereas the time here is any time you choose to be appropriate for your problem of interest, right? And so if you remember the second lecture of Professor Kolbe, he showed this nice linear viscoelastic spectra of ionomers and introduced different characteristic times. You may remember there is a time related to the dissociation process, and then a terminal time, right? So I have two times here, and so I can define two Weissenberg numbers. And of course, now one can go to the linear response. You remember the linear response is these oscillatory measurements, okay, and define the Deborah number, where the only difference is instead of using shear rate, I use the frequency of oscillation here. And of course, this is not a photo of the prophet Deborah, but is of Marcus Reiner, who was the rheologist who introduced this concept. So then, in those cases, I have diffusion, I have convection, and I have observation. Those are the three important elements. If you are interested to learn more about Weissenberg and Deborah number, and so there is this little essay by John Deely that you can see there. So now, why are these things important, aside assigning dimensionless number? Let's go back to Ralph's first lecture. You may remember he showed you this linear viscoelastic spectrum, and you may remember that that was from a Maxwell model. The actual experiments were done with surfactant worm like Meisel. But you may clearly remember, and this it's exactly from his lecture, that this is the normalized moduli with respect to the plateau. That's why this value here will go to 1, and this is the normalized frequency with lambda. Lambda is a characteristic time. And guess what? The peak of G double prime, you may remember the Maxwell model, and the crossover of moduli coincide with omega lambda 1. So that's our Deborah number. And so basically, all we learn from this is that at Deborah numbers above 1, my observation time, okay, is much smaller than the relaxation time of my system. So then I can see a fast response. The system doesn't have time to return to equilibrium conformation. Okay? And so this is related to the solid-like response of my material, where G prime is much larger than GW prime. On the other hand, low Deborah numbers is exactly the opposite. And then in the vicinity here, I have what I call viscoelasticity, and that's really where the action is. So in this respect, this plot here can be considered as mechanical spectroscopy, because I change the Deborah number, I change the frequency, so essentially I change the characteristic interrogation time, and therefore the characteristic size scale, which is responsible for this interrogation. Okay, so these are the usefulness of these dimensionless groups, and one can do, of course, the same with the Peclet and with the Weissenberg number. So this is a little test for you, not for now, but I put together here the different forces. We have discussed the gravitational Brownian, of course, Stokes, and we have also, of course, the electrostatic and the van der Waals. This is crude expressions, okay, but you have here typical characteristic numbers for different parameters, and then you can check for yourself the ratio of the two forces and see how important this is in order to understand exactly the state of your system. Okay, so now, with all this background, we go toward Haass spheres, and we are now back to 1968, when I guess a few of us were interested in colloids at the time. Certainly I was not, although probably I was playing with them. This is visual observations by Peter Pusey again and Bill Van Meegen. So they started preparing PMMA suspensions in different volume fractions. And so you increase volume fraction from number 1 or 2, whatever is there, to number 10. And so you see what's going on after 1 day and after 4 days. And what you clearly see is from the Bragg peaks here, the evolution of crystalline phases. And then as you keep on increasing the volume fraction, at some point, again, they are lost. Okay? So there is a way now to define the phase diagram. And so by doing this carefully, considering the fact that you have to wait over time, because of course when you have phase transition, there is kinetics, etc., okay? And one can define a phase diagram. And this is what we call a complete phase diagram of hard spheres. This is for the monodispersed case. Low volume fractions is a fluid regime. Eventually, at the very low is what we'll call a colloidal gas. So then we start the crystals appearing, as you saw with the Bragg peaks. So there is a fluid crystal coexistence, a crystallization regime. And then at this magic number of 0.58, which was first found by simulations, you lose the glass, the crystal, and you form a glass, right? So basically the material becomes amorphous, so you might have seen that you lost actually the Bragg peaks, and then eventually you have again the reappearance of a crystal, and you go all the way to 0.74, which is the maximum close packing, right? So this is again confocal microscopy image of a fluid. This is a glass, and this is clearly much more organized. Either FCC of eventually here hexagonal close packing arrangement of hard spheres. Right. So, yeah. Oh, yeah. Sorry. It is preferred thermodynamically. The glass, as you know, is never thermodynamically stable. It is preferred. And the reason for this, for me, the easiest way is something that Bill Russell and Alice Gast wrote. And it relates, of course, to the fact that those are entropic objects, right? And entropy is the only thing that is important because the energy here is constant. And so what they wrote, I like very much, that's why I would like to mention this to you, is that imagine that you have school children in two different instances, right? It's the same number of school children. In one case, you have basically you have them organized in line because they are ready to enter a school. So this is basically, in a way, each one has a restricted degree of freedom. And in the other case, they are the same, but they are basically under intermission. This is the glass, right? So then in this case, it's exactly the opposite of what you ask. The preferred configuration is that of the arrangement because still, despite the restricted degrees of freedom, on the average, there are distances between the rows, and so the degrees of freedom are more for the crystal. This is why the crystal here prevails. But as you increase the volume fraction, okay, these degrees of freedom become more and more restricted because you have to add more and more rows, okay? And so in this way, the amorphous arrangement is preferred, okay? So this is the reason. So in this respect, the glass will be preferred, okay? Now, if you wait for much longer time, there is recent work, again coming from the same, from Kww and so on, telling you that at extremely long time, indeed, the crystal may reappear. Okay? In the previous, sorry? The previous slide. Yeah. The range of volume fractions, the highest one is above 58 here, right? Right. Sorry? Sorry? Right. But you see what happens. Okay, this volume fraction is higher than this one here, right? This range of this is different volume fractions. Okay, I don't remember by heart now, which is okay. Yeah. So in a way, I would give credit to what you say, because and I think people now agree that the fate of the glass is eventually the crystal state, right? Okay. But there is this intermediate regime where, as you add more and more particles, the system would prefer to stay amorphous.
Can you briefly explain why some of the coefficients, the clear crystal and the crystal is at bottom, while the other crystal?
I think it has to do with the volume fraction, okay? And the way, for example, here, the glass starts from the bottom. Eventually, you see the whole thing really covers. What happens is that the amorphous phase starts developing here at the bottom, right? And so this is maybe related to the fact that here you have extra boundaries, right? So everything starts from the bottom and it goes up, okay? Yeah. That's a good question. You start from, let's say you start from here, right? Or you start from here, say, whatever, right? And you decrease the density, right? The real answer is that I don't know, but I don't think that it's necessary. Okay? I don't think that's necessary. So in other words, it's not a fully reversible process in this respect. And the reason for this is that the glass is a metastable state and it's time dependent, and it depends on how really you introduced on this. But as I mentioned, I'm not aware actually of such an interesting test. I don't know if in simulations this has been done. Okay. Yeah, I think we saw this one. So now, if you introduce polydispersity in the system, so in a way, this crystalline part is basically masked. It's more difficult for the systems to organize. So it's basically a super cool region, and eventually you have glass. The glass always, it's clearly defined at 0.58, and we'll come back to this. And eventually, at 0.64, you have the maximum close packing for the polydispersed system. Right. So this is one-dimensional diagram for the reason that we mentioned. It's purely entropic system, okay, a thermal. And the effect of polydispersity is basically to really lose the crystal phase, as one actually also expects. So now here is a question for you. I have a vial here, it's a glass vial, and I introduce a paste which is colloidal glass, right? And I can see this because, for instance, the standard test I do is I turn this upside down, okay, and it stays where it is. So how many glasses I have into this? The question is the following. I have this vial, right, that any lab has. I introduce a colloidal suspension of PMMA particles at, let's say, point fraction of 0.6, right? And so my question is, how many glasses do I have into this vial? Sorry? Yeah, well, it's a glass vial. 2. Other answer? All right, 2 is, of course, the logical answer, but remember, this is PMMA hard spheres, and PMMA has a glass transition, right, okay? So the hard sphere itself is a glassy polymer, right, at room temperature. All right. Oh, yeah. So now, let's remember the diagram I show you. So let's try to make the systems soft. And so for us, softness means you go to a super chemist, okay, and you ask them, can you, Chris, make these things for me, and so on. And so the chemist will make them for you. And so now here you can have what I like to call mechanistic view of softness. Here is our hard sphere here. Typically, as I mentioned, is submicron. Okay, I'll go all the way to the polymer coil. Remember, the size scale is much smaller. Okay, and of course, aside the difference in size scale, we know that our polymer in solution will go all the way to the melt. I'm talking about a classic linear flexible polymer like PMMA without anything interesting, whereas the hard sphere will organize into different states, I would say in general, either thermodynamic or metastable. In between, if we start from here, we can have vesicles, we can have soft spheres which are stabilized with what Professor Colby doesn't like to call amphiphilic system, right? And then we have microgels, grafted particles, and stars. Okay. So now, what is a microgel? We know, right? It's a polymeric network in the form of a sphere. So, for example, you are going to take a few polymers, you are going to put them in conditions of batch solvent, they will shrink, and then you are going to cross-link them. And those of you who do chemistry, they know better than me how to do this. So now, that means that I can think of a simple way for a single particle to somehow say something about its softness by considering the elastic energy. So then, as you learned in the lectures of Professor Rubinstein and Professor Grossberg, so here this energy is basically kT, whereas here it's pretty much infinite, right? And so it's here, it's very high. This is the size of the particle. So then if I go to the emulsions, so then the interfacial tension is important because that's what really stabilizes, and we heard this nicely from Federic, how this happens. If I go to the microgels, what is important here is the cross-linking density, right? If my cross-linking density is infinite, so then basically I form a hard sphere, right? And so the way I described it is by the number of monomers between two cross-links. This is the monomer volume, and that's the size of the particle. And then when I go to these grafted particles, then the number of the grafted chains is important, and I use for simplicity stars simply because they are simpler, so the number of arms themselves is sufficient. And so then if you do just simple estimates of these things, you see how the softness goes. So you go from, of course, the really hard material. So now introduce the softness not so much in terms of interaction, but in terms of the ability of the particles to change shape. And so you go really to the very soft systems. So that suggests that there is a zoo of particles, which I can call soft. And the question is, what can I do about this? So before we answer the question, let's now see what happens when I go to the end of the spectrum. You remember the one-dimensional phase diagram, and I have the regime where I have this close packing, right? So then I will say I will put soft colloids at contact. So then if I have hard spheres, you have something like this, right? So the contacts are basically just 1 point per contact. But then if I have emulsions or vesicles, I can deform them. And so you can see this example here from a confocal microscopy, and I can form these facets, right, all around. So then this is in a way two-dimensional, right? And so this is relatively recent results using what they call super-resolution microscopy for a PNIPAM particle. So PNIPAM is poly N isopropyl acrylamide. I'm Greek, so I have to pronounce it right. Okay. So this is in a way a grafted microgel, right? So then dangling ends are important. And in these images, one can make some observations. This is increasing the effective volume fractions. So you can see that there is certainly some regime of interdigitation, okay, because of these outer layers. And this becomes even more apparent here. But then, of course, you can see that there is faceting, okay, obviously for clarity, only the two particles are shown. You can see the facets which are formed, right? And then, of course, you can see that there is compression as well, right? Because this is smaller than this one here, right? So that's why in the systems we have deformability, okay? We have interdigitation, and then we have compression. I prefer to separate deformability for compression because obviously in emulsions you cannot compress them. All right. So this, yeah. The hard spheres? Not in this context, all right? Because here now we don't talk about the potential, we talk about basically the response, the shape response, if you wish, of the particles at contact, because that relates to something that I'm sure you know, the jamming regime and so on. What happens when you go at the end of the glass regime, right? The other thing, and I'm not sure if I answer your question, that's why I need to give you the other information. Now, if you have an experimental hard sphere like the one I mentioned, you may have such small effects, like, and actually this is one of the issues that people have dealt with, also in problems related to something that I hope to cover, the discontinuous shear thickening, when you have these layers, which of course then when you bring them, I don't know, if that, probably that's what you meant, right? So then you have some kind of compression of this grafted layer.
Right, no, I mean in general when you think of a system being soft,
Mm-hmm.
I mean at least you would naturally not think it's because of the soft particles, but somehow the collection of the particles are behaving more.
Sure. Oh, yeah. Right. So then you refer probably to the caging and so on of this, so when it's a collection of parts. Yeah, we'll come to this later, I hope. Okay, so now what I'd like to show you is one of the many ways to somehow try to get paradigms of model examples out of this in order to study the effects of what we call internal particle microstructure on the properties. This is really what is missing in our view. So then I will refer to Tom's nice lecture when you may remember he talked about star polymers, for example, 3 or 4 arms or 5 or 6. And then if you remember, he said that in this case you don't have adaptation, but you have the arm fluctuations, and I don't have a jacket with me, but nevertheless, the characteristic time is basically the exponent of the number of entanglements per arm, right? Simply because this is a stagnation point. It's basically a wall. And so this is from the Rubinstein-Colby book, but it's data by Linden Archer. And so we can easily now see that this data here refer to the linear polymer, say the molecular weight of the arm, with a clear plateau and the terminal crossover. This is moduli versus frequency. Shifted frequency, you may remember it was discussed recently. But then the arm, because of its effort to do this, which obviously is entropically unfavorable, it takes many trials to do it. And so then eventually it does it, but look, the GW prime is extremely broad. So this is known. So now what we want to do is to increase the number of arms. And actually chemists thought about it long ago. And so you see that you go now from 3 to 128, and today people exceed 1,000 arms. And so now there are two aspects for this. As Professor Maciejewski nicely explained yesterday, if you want to do this with utmost accuracy, it's very cumbersome and it will take I don't know how long. And of course, you may achieve this. That was done at the time with high vacuum anionic synthesis techniques, all this glass blowing and so on, super clean solvents, etc. The advantage is that you have monodisperse systems. Monodisperse means that the weight to number average molecular weight have a ratio which is below 1.1. So this is really the case that we'll talk about. On the other hand, the idea is that, of course, when you study this, then you can go back to simpler, in a way simpler, right? ATRP methods, and then you can have systems which are equally good, but perhaps a little bit larger, dispersed and so on, and perhaps they have similar properties. Nevertheless, when you go from 3 arms to more than 30, which is this creature here, so then you have this first part, which is pretty much what you saw. This is the glass here, the polymeric glass. So you have the plateau and then it drops. So this is the arm relaxation. And then you have a second mode that relates actually to the fact that this is now a colloidal object, right? And so relaxing the arm, it's not sufficient for the motion of the center of mass. You need actually this kind of gauge escape, which relates a little bit to what you mentioned, and we'll see this in a minute. Okay, so this is now the stars. And so another model particle is microgels. And why are these models? Because here, by changing the number of arms, you understand I go from a polymer toward eventually a hard sphere colloid if my functionality is infinite. And here, by the same token, by changing the grafting density, I will go from a simple polymeric fluffy network to something which will be eventually hard sphere object. And so in both cases, osmotic effects are important. And I remember what Professor Grossberg described with osmotic swelling in such systems in his lectures. Okay, so now if we look at a little bit more detail, and more of the details are in the reference, this is a cartoon representation of a star in a good solvent. And so what you see here is your beloved blobs, right? And so there are two reasons for them to appear. The first is geometric, right? Because obviously as you move from the center, which is here, to the outer part, the degrees of freedom are different of the polymer. But typically, and this is nicely described in the classic work of Dao and Coton, again here in France, is that there is this regime where the blobs are ideal. And so that means that if you bring stars closer together, there will be no interpenetration beyond this red area because it doesn't really reduce the free energy in the system. Whereas the outer blobs feel excluded volume interactions. And so those are the ones where the activity takes place. So now I'm going to bypass some details and just tell you that as one can understand, the size of this creature will depend, of course, on the size of the number of the arms, because when you put more and more arms, that's something that the chemist will do for you. You understand that the arms will be more constrained, so then there will be a little bit of stretching, which is described by this factor f to 1/2. And because I mentioned that you put this in a good solvent, you recover the 3/5 power law, the Flory exponent, in a way. So that's a simpler way. Of course, one may also understand, and I only mention this, that the monomer density changes going from the center to the outer part. It drops. So now, with this in mind, people have developed a purely repulsive coarse-grained potential, and I'll show you here only what it does. So the idea is that those creatures will come close together, they feel repulsion, so then they will repel each other. But it's based on ideas by Winton and Pincus on stretched chains coming close together. And the key concept here is that the only parameter that controls this potential is the number of the arms. And what you see here is when the number of arms is very small, you have a very, very soft potential, typical of what you would expect for a 3-arm star polymer or 4, or even linear coils. And then the potential becomes steeper and steeper as you increase the number of arms, and eventually it will be basically hard sphere, right? So then this suggests that if I go back to my chemist and I ask for such systems with changing functionality, I can also tune the potential and therefore eventually the properties. And yeah. No, this one here is, I didn't mention because of time, this here is a potential, coarse grain per interaction potential. It's a model, right? Okay. And this is due, the main person here is Likos, and actually this is the reference, this PRL here. However, there are simulations which are in full agreement, and there are experiments which are also consistent. Okay. In fact, in that reference here, the 1998 PRL, there are experiments with neutron scattering on the structure factor by Richter's group in Germany. And so then the structure factor extracted for that potential is in perfect agreement. Okay. So in a way, one can say that this is, I think, reasonably well established. So now, if we go to the microgels, so then Ken Schul yesterday discussed nicely, I think at the end of the lecture, the Hertz potential, because you have contact, and this is what people also use for emulsions, and this is the origin for describing the interaction in these systems, right? And so typically, again, you have a significant softness, which depends on one parameter, and this is the number density of the crosslinks. Okay, so now this allows us to draw, again, one-dimensional diagrams for the different systems. So let's start with the polymer coil. The polymer coil, there is, in this respect, nothing interesting. It remains in solution in the same solvent conditions, right, all along, right, up to the melt. Let's go to the hard sphere. You remember we had the fluid state, Then we had the glass. So this already suggests that since I don't say anything about crystal, perhaps this is slightly polydispersed. I call it here thermal glass for reasons that I will explain in the end. I hope I will have time. And eventually, you can have crystal when you have hexagonal cross-packing and so on. And so then you have the macrogel, which is somehow in between. Okay, there is a glass transition, almost at the same volume fraction, but this depends on a number of parameters, as I have indicated. You have all this regime, but then there is a second transition to what we call jumped glass. And I think this is an interesting analogy to granular material. So thermal glass means that my constrained particle still does Brownian motion. So then KT is basically responsible for the properties. Jumped glass is at what I already showed is contact. So basically, there is no anymore KT in this respect. I have really fastening and deformation and elastic contacts, basically, that are important. So now the star, it's a bit more peculiar case. I go from the solution to glass in general, and I will try to show you at least the signatures that dictate the difference, right? But as I write in the end, distinguish thermal from jumped glass, it's not easy and has not been resolved. So now, here is a question for you. What should I care about? Why do I bother you? It's Wednesday morning, you know, it's great to go to the beach. Why should we bother? Let's look from my perspective. I mean, I'm doing rheology, so then I go back here. Look, Carbopol is really the rheology's paradise, right? There is significant improvement in the field with Carbopol particles, which we don't, or certainly I have no idea what they are, right? Also, there's some fantastic poster here on carbon black, right, with fantastic properties, very interesting. Why not use these materials which come in abundance and talk to the chemist and finally, in order to have a few milligrams or a few, certainly less than a gram, and really deal with these things? Absolutely. I think the only way, you remember the lectures of Professor Colby and Professor McLeish. Right? In order for us as a community to arrive at a point where we understand the raptation and the all related processes and so on, it basically is done by using model systems. So the problem with this here, and it's not a negative, I think it's a challenge actually, is that you can explain things at a mechanistic way, phenomenological, but not deep relating to interactions and to molecular features. And so if you are interested, as some of us are, in molecular manipulation of these things, so then saying how I can change things without affecting the environment, so then you need to go through this step. Okay, so now with this, I would say partial background, remembering that at high fractions, high volume fractions, I basically have to deal in part with some crystalline phases, but basically with these metastable glassy jumped phases. Let's see really how I approach this and what some properties of this are. And to do this, we need to start by introducing the techniques. So Professor McLeish, you remember, introduced the origins of rheology through Bede in Durham. But of course, you know, I can't help it. I will go a few centuries before. I would dare to say that's the most recent photo of Heraclitus. You know, well, as you know, one of the things that Heraclitus said, admittedly, as it turns out, not in the context of law, that's important to say, is that everything flows. And this, by the way, is the logo of my favorite professional society, and also, I believe, Professor Colby's favorite society. And it's written in proper Greek. You know, it took many years to correct, to add this little thing here. Those of you who are into classic, you know, you need to have this little apostrophe at there. But anyway, now on a more serious note, Pandari. Pandari. All right? Yeah. Okay, so I'd like to make a connection with Professor Hui, who made a very nice, rigorous introduction to the continuum mechanics, which is the background of the measurement. And the main thing to remember is that you have this cubic element here, and I think others showed this as well, and you have the stress tensor with diagonal elements, which are the normal stresses. For example, I take this area here, and I pull, and the off diagonal, which is the shear elements, I really shear this area here. And then when you deform it, you can write the deformation tensor. So now from this, we are going to stick to what Ralph showed. We can define the shear rate is the velocity gradient, okay? And for simple shear, which is basically the two plates with one plate moving and the other being immobile, I have what we call shear stress growth function and shear stress growth coefficient, or if you wish, transient stress and transient viscosity, and I integrate my modulus over all times the shear rate and the time, and here I divide by the shear rate, so this is Newton's definition. So now things are simple when you know this part, which is the relaxation modulus, and that relates to the Boltzmann superposition principle. So this is basically the main thing. So now, what do? You go to your lab and you put your sample in the rheometer and you measure, right? As somebody mentioned here, you are aware that there are two kinds of rheometers, stress control and strain control. In a stress control, I put my sample here, and all the action takes place on top, where I have both the motor and the sensor, if you wish. Okay? And the nature of this instrument is to control the stress that it's imposed and to measure the deformation of the rate. Okay, and so this is always what we do. And as Professor Kolbe explained nicely, of course, we only do things on rotation, at least with those instruments. So now the strain control has two different drives. Here's your sample. Here is your motor that will create the deformation of the shear rate, and here is the transducer, the sensor. Okay, and this is good for rate control tests. So now those are what we call single drive, and this is to contrast with a twin drive. So what you can do, and this is what the vendors do in order to sell you more expensive instruments, is to take two stress control rheometers, one upside down, and here, well, here they are, one here and one here, and you do this thing. But then you can counter-rotate them, and then your shear field is like this. All right? So, and the question is this useful at all, or is it just a waste of money and time? You know, right? Of course. Because this is a stagnation point, right? And so that's what people use often in order to make observation and so on. Okay. So now the next thing is to choose a geometry. And so this is a partial laundry list of geometries. Some have been discussed: cone plate, parallel plate, coaxial cylinders in different ways, Mooney cells, and torsional, because somebody here told me that they do torsion tests. This is for solids. It's mainly liquids, but can be also, in some cases, solids. And of course, since I'm here, I cannot help it citing another important French physicist, Maurice Couette, who, according to whom the simple shear cell is basically named, either what we call, where is it here, plane Couette or cylindrical Couette devices. Okay, so now the next question for us is, oh God, why use different geometries, right? All right, so I'll let you think about an obvious answer can be, oh, maybe sample amount, I don't know. But let's look now at the Conan plate, which is a standard geometry we like to use. Here is my setup. This is a plate, this is a cone. Say it here that my cone rotates, so the plate has a sensor, it doesn't matter. You know, there is a certain angle here, and so of course there is the R. So basically, to solve the problem here of stress and velocity distribution, you use spherical coordinates, because it's the R phi theta, or R omega theta coordinate system. My shear rate will be the velocity gradient in this direction, and I can define like that. So that's my velocity. This is the length, and therefore, of course, for very small theta, I can simplify this like this, right? So why is this important? This is important because my shear rate does not depend on the radial position. It's uniform throughout my sample. That's really the reason why people like to use cone and plate. This is not the case for parallel plates, which I'm not going to show here, but people can easily check. And then the instrument will measure the torque for you, and from the torque, you can extract the stress, right? And so this is basically how this works. And so then I have here the sample loading, which now you understand why we never use here. If you do trimming in your lab, be careful, right? Because you are going to change the boundary conditions. It has to be part of a sphere. And this may be detrimental, or maybe not. Okay. So now here's the question. We say so many things about shear rates. A great poster here with shear rates. What is 1,000 reciprocal seconds? How can I realize 1,000 reciprocal seconds? Very fast, that's for sure, I agree. Voila. Have you ever done this? If you haven't, wait to get married. Your wife will ask you to, okay, do this. How fast can you do it? Don't tell me, you do it faster than me, but I'm not going to do it faster than 1 meter, right, per second. So basically, that's what we do, right? And so, what is the thickness of my layer? Come on, what is the thickness of the paint here? Don't tell me 2 centimeters. Yeah, I'm an engineer, so easy things. 1 millimeter, right? So then, this already, 1 meter per second, 1 millimeter will give you 1,000 reciprocal seconds. Okay, that's more or less to have an idea. And then you understand where the paint you're going to use is very viscous. You see how difficult this is, right? But then you run into other problems there, which we may or may not have time to go through. Okay, so then the other thing that we do is light scattering, and Anib gave a great description of scattering techniques. I'm not going to add anything to this, only one little thing. So we're going to send a laser beam to our sample, and then it's going to scatter at a certain angle. You remember the scattering wave vector, the refractive index, wavelength, and scattering angle here. And you have a scattering pattern, which then you analyze, as we'll see in a minute. So this is dynamic light scattering. Also, Tetsu discussed this very nicely. The only thing I would like to add is that light is polarized, so then you have vertical polarization of the scattered and of the incident and of the scattered light, right? Only in these conditions, it turns out that really you probe what we call concentration fluctuations, which then will give rise to the diffusion coefficient. If one of the two polarizers is horizontally polarized, so then you are sensitive to the anisotropic fluctuations, which have to do with the polarizability of your molecule. And so it's a completely different thing, which we don't discuss here at all. For the little data I'm going to show you, we worked on the single scattering limit. So that means simply transparent sample, and basically nearly all of the intensity is scattered. Okay, so typically this is the scattered intensity, and what you do is you take the time autocorrelation function, So that means you take different time segments and you make their correlation here, take the average, and you normalize them. And so this is the intensity, and this can be written in this form, where this is the field, the electric field that you get from the photomultiplier, which is typically your detector. And so this is the so-called Seeger relation. Okay, so now you can show, actually Tetsu showed very nicely, that this here is related to the mean square displacement, and much to the disappointed of Shura and Ralph, I thought whether I should remove this, but I kept it. This is the notorious Kww coefficient, but I will explain why for an experimental this may or may not be useful. I would dare to say may, right? So this is basically this simple form. So then this is your correlation function. There are different ways to show it. We like to show it in a linear log scale. And so it has this form here. And so basically you're going to fit it with this exponential here and then extract the characteristic time. Okay? So now why beta is potentially important? Because as correctly put yesterday or the day before, this should be an exponential process. So beta should be 1. Experimental, it's never 1, right? But as long as it is above 0.8, 0.85, so then we say, for us experimentalists, you know, it's fine. You have a single process, this is diffusive, and then you go on, right? The other thing is that if it is very broad, I'm talking about something like 0.6, 0.7, 0.5. So this means clearly that this thing doesn't make any sense, right? So what do? You break it and you fit your function with 2 exponential or more. And actually there are packages, the most well-known that some of you may know if you work with this. It's called Contin, okay? A package which basically allows you to determine with just one regularization parameter the distribution of relaxation times. So now I did mention you get diffusion. So now you understand that you cannot get diffusion by measuring only at one scattering angle, right? So you can to scan the angles or the Qs, okay? And then see how your time depends on the Q square, okay, in order to really get the diffusion coefficient. But once you get your diffusion, so basically a coefficient, you are done. So now I'm going to make a little step and go to dense suspensions. So you remember is this regime of supercooled conditions approaching the glass. So now every particle moves but feels somehow the constraint of the neighbor, and this is exactly the case of the thermal glass that we mentioned as well. So now this means that if this is here my test particle, okay, this test particle will be caged within an effective cage constraint of neighbors, and so then you understand that if I'm in prison, I can do little moves, and at some point when the door opens, I escape, right? So that's the thing. So this idea was put forth by Frankel, not Dan Frankel, by another one I don't remember, physicist long ago, and Peter Pusey actually advanced it a lot. So then that means that I have 2 characteristic times. I have what we call the in-cage diffusion and then the out-of-cage diffusion, okay? So let's see if my little cartoon, okay, prepared by the student, of course, works. So let's watch this guy here, here, and then here, right? Okay. Voila, this is in-cage. The cage remains intact, but there is a diffusion, okay? We're going to call this short-time diffusion. And so this is the cage escape. But I think it is already instructive to make analogies. You remember what Professor McLeish told you, okay? He told you that in entangled polymers, I have the tube, right? And the eventual relaxation is the tube escape, right? In the way that he beautifully described. But within the tube, okay, there is the effective Rouse motion and so on, right? So The advantage of polymers is that you can do mean field, as our bright lecturers explained. In colloids, you cannot do mean field, and I guess one reason is that you have very few partners around, right? The coordination number is small. Okay, so now here are some data. The data are, of course, from Puse's group at the time. So that's the intermediate scattering function, okay? And this is hard spheres, experimental hard spheres. I increase the volume fraction. You see I have one relaxation process. And as the volume fraction increases, I have the evolution of the second process, and eventually pretty much no relaxation, okay? So then, in a nutshell, this gives me a way to drive through the entire phase diagram, right? From the dilute gas to the concentrated to the glass, right? Which is non-ergodic here, right? So now the way this is done, and that's another important parameter, is by looking at the product QR, right? And you remember we discussed about the time, the dimensionless time. This is dimensionless scale, right? Because now the Q is the characteristic size. This is really, I mean, the technique is called photon correlation spectroscopy, right? Because this is basically the size scale that I probe, right? So QR larger than 1, it means that I look within my R, right? Whatever R is. R here can be the gauge, of course, right? Okay, so now, with this in mind, let's go back and measure shear viscosity. This is a particular example. I will leave the details for you, but this is now relative viscosity normalized with a solvent as a function of the Peclet number. And when I see this, this is exactly what Professor Colby showed you, if you remember, right? And if you remember, he told you when you do this properly, you will do everything from transient measurements, and then you are going to put the data. I don't say that this was done like this, but this is fine. So then I have a low Peclet plateau, low Peclet number plateau, which is basically my, what I will call my equilibrium structure. This is the thermodynamic limit and gives me the zero shear viscosity. But then if I keep on increasing the shear rate, interestingly, I can reach a high rate limit, and this is what we call the hydrodynamic limit. And the cartoon here shows what we expect it's happening. So the particles are basically organized in flow, and depending, of course, on the fraction, there are different levels of organization, but there are basically stripes of particles in flow, and there are plenty of simulations, but also real confocal experiments that confirm to this. Point is that this is equilibrium, thermodynamic limit, this is out of equilibrium, hydrodynamic limit. So now you can fit the data, and this is one of the many empirical models, but it's used routinely in this field. The cross model, this is the high limit, this is the low limit, that's the shear rate, and this here is your thinning exponent, right? Shear thinning exponent. Okay, so now the next question is to see how this relative viscosity depends on volume fraction, and it's not surprise if we say that the zero and high rate limits have different volume fraction dependence because they reflect different behavior, and so this one diverges before the other one, and we'll see now exactly how we can see this in a little bit more detail. So I go back to the low shear limit, and this is plenty of data, including simulations. The simulations are done basically by Foss and Brady. At low fractions, I have my Einstein limit, right? And so here's a question for you. What is the 2.5? Sorry? Oh, this is dilute. Look at yeah, right, yeah. To help you answer, I added here Ralph's name. Well, think about this is relative viscosity. If I put 1 here, it will be specific viscosity. if I divide by phi, it will be intrinsic viscosity. So that's the intrinsic viscosity of hard spheres. All right? That's the way to look at it. Sorry? Yeah, of course, it can change. Right, of course. Yeah. Oh, yeah. Oh, no, here, no, because this is the ideal, right? This is the ideal case. This is Einstein's relation, right? Yeah. Of course, in the experimental system, when you have your little layers and so on, there can be an effect. Yeah, of course. Yeah. Okay. So then the next step is to increase the volume fraction, and then when you increase the volume fraction, you have a band. Yeah. We'll come to this. This data, thanks, sorry if I didn't mention, is for hard spheres. This is all experimental hard spheres, right? Yeah, thanks. Yeah, when we increase now the volume fraction, we start having binary interactions. And here what is important is the hydrodynamic effect. And George Batchelor worked out this. And, oh my God. 3 to 5. Okay, sorry. Okay, so then, sorry, c'est la vie? Okay. It's okay. Okay. Can I have 5? Okay, so this is the hydrodynamic effect. And then for the rest, which is this one here, it's the approach to glass transition. Typically, you expect that the divergence occurs at glass transition. This very much depends on the graphing layer. It's very critical. And this is one of the many empirical laws, and I chose this one because it's Quemada is from France again, right? So, all right. So then I will do things fast. Sorry about this. I want to make an historical note here. We call this Stokes-Einstein-Sutherland because the physicists, I'm sure they know, I didn't, but I found out from John Brady. William Sutherland was a Scottish who lived in Australia, and at the same year, the 1905, he developed the same equation with Einstein. But, okay, so then we try to pay justice here. So this is Stokes-Einstein. You have seen this before. We'll go now fast. So this data now is viscosity and inverse diffusion. This is shear viscosity, so there will be long-time diffusion, and the divergence along with simulation data, with scattering, of course, occurs at glass transition. Now, if you do the same thing with the high rate viscosity and the short-time diffusion, you have the same behavior, but the divergence will occur at the maximum close packing. That will be the difference, really. Okay. And I need to speed up and address your question. Now, with soft particles, a fundamental question is how you define volume fraction, okay? So you will see things in the notes. The simplest possible way is C over C star. Come on, everybody can do it, right? Okay. So then you remember I have this nice star polymer. I know all the details and so on from a chemist. After all, why do I do a model system? So then I get C over C star, okay? This is a way to do it. Another way to do it is to use the Batchelor expression and assume that my volume fraction, which I call it effective, because I define it, is linearly proportional to concentration, mass concentration. Obviously, this is not correct, but for low concentrations, it may work. And yes, it does, right? This is my volume fraction. This is the concentration. This line is basically this linear dependence. But then, as the concentration increases, the increase of the volume fraction is smaller. Why? Because you go back to the lectures of Professor Rubinstein and Professor Grossberg, you have osmotic effects. And so then when you have the contribution properly taken care of the osmotic effects, then you see this behavior here, which I will have, I'm sorry to pass quickly, so that I make a point here. And the point is that this is now viscosity and diffusion together for soft particles, okay? So this is hard spheres, this is polymers, and this is different soft spheres. A point to make is look at this. Okay, this is a particular class of grafted microgel particles, right? Okay, so why does this happen? And this also agrees with simulations. Okay, can you think why you have this bump here? You have osmotic compression, okay, of the particle, because as you increase the concentration, the osmotic effects become more important, right? Okay, do you see anything else which is peculiar in this plot? Look at the x-axis. Your volume fraction goes beyond 1, of course, right? Now you understand why, huh? Because the way we have defined it is you can have overlap or compression or whatever. Right? Okay, so now I will leave these funny things with. I apologize. I know this is. I want to make a point here and refer to Tadeusz Pakula, who was a great scientist, who is the first, to my knowledge, who really simulated this hopping effect. That it's really related to what. I mentioned before the caging. This is a particle that does this in-cage rattling, okay, and at some point it hops out and goes to another cage and goes out and so on and so on, okay. This is exactly the way we're set to understand the relaxation colloidal gases, and of course there are experiments for this. Let me just, I really apologize for the time, compare now a fluid state, an entropic glass, and what I call a jumped glass, right? So this is the same particle, okay? It's a microgel system. Actually, this is from Michel Cloat, so well-defined microgel system. Oops, sorry, Costantino. Okay, so you increase the volume fraction, right? And so you go from a liquid behavior to a glass, and then to a jumped glass. So then the modulus goes up dramatically. But look at the values. They're barely kilopascal. Compare the colloidal glass to the polymeric glass of Professor Colby. It is gigapascal, right? So this is one of the many reasons why colloids are nice, right? You can easily manipulate your glass. Let me jump into the last thing. Well, obviously, the behavior, the details of the jumped regime, so how the modulus with dependent concentration are unique to the different types of softness, so microgels and stars, so basically compression versus interpenetration. I'm sorry that I want just to mention a last thing. You have also some questions to look at if you want to induce vitrification and heating. Let me go to this. This is depletion interactions. Okay, so now you have your particles, hard particles, and then you add smaller particles. In our case, it will be non-adsorbing polymers, right? And so what happens is that when the two particles are together, there is an effective overlap volume, which I show here, considering that a small particle is excluded from a region around this hard particle, which is the size of the polymer. So then the polymer cannot enter here, right? It costs too much entropy to do. So the particles will accumulate externally, right? And so that basically maximizes the degrees of freedom in the system, right? Compared to two independent particles with their shell around it, these purely excluded volume interactions. And so then, by definition, this creates an osmotic force into the two yellow particles. And Sakura and Osawa were the first to describe this and came up with the depletion attraction potential, which this one here is hard repulsion, but before this you have this attraction. And so there are three parameters. Obviously, the hard part depends on the size of your hard sphere. You have a range of this attraction that depends on the size of the polymer, and the strength of the attraction that depends on how many polymers you add, right, on the concentration. This has led to this diagram, and if you are interested, this is the paper to look at, the paper from the Edinburgh group, right? And so you have here increasing particle attraction and volume fraction, and we only focus in this regime here, all right? This is the 0.58 when you have a glass. Glass means that you have this caging effect. And so now, when you add particles, what happens? When you add, polymers, what happens? The particles will start bonding. And so here is the way they bond, but by bonding, okay, means that somehow a particle will bond to another one, but it will create a little bit more free room. Okay? In this respect, there is some opening of the cage, right? And so you turn into a small liquid pocket. To have this, you need to have a narrow range of polydispersity, which we can discuss only if you're interested. And then on increasing, basically, the osmotic pressure, eventually you have what we call attractive glass, right? So that was the origin of two different glasses, repulsive glass and attractive glass in the system. And of course, the properties are uniquely different. Okay, I'll show you here mean square displacement, right? This is the classic repulsive glass. Okay, the attractive glass has, of course, a smaller mean square displacement, and of course, the liquid flows. And this is finishing up. If you do linear rheology, so you start basically from repulsive glass. This is G prime and G double prime around 100 Pascal. You increase attraction this way, and then this way up, and you increase the modulus in the system, whereas more or less the rest is pretty much the same, except that the G double prime has a slightly different shape. And I think this is it. You see how the modulus now changes as function of the effective concentration of the star. If you have, and that's my last slide, if you have softness, okay, sorry, right, so then instead of having a re-entering attractive glass, because you can basically compress your soft particle, you end up with forming a gel, right? You basically reduce so much the fraction of the soft particles that basically you are in the attraction regime that creates gels. And I'll let you with a summary. So hopefully we saw how you go from hard to soft. What are some ways to manipulate interactions, also at molecular level with the key parameters, and a taste of cages versus tubes. Sorry for the time. Thanks very much.